Yeah, so please stop by if you have any questions or want to discuss other things as well. So what I wanted to do today was spend probably the most of the class today discussing and about energy band diagrams in various situations, and then also introduce you to the way I'm starting out is you should be analytically able to, using paper and pencil, you should be able to figure out things like depletion weights and whether there will be formation of electron 2D electron gases or not. All this stuff you can actually do analytically, and that's where a lot of the power of understanding things intuitively comes in. But once you get to the point where you've actually designed something which has to operate very accurately, you need to start using maybe a little more accurate numerical tools after you get a feel for it analytically. And I'm going to spend maybe the last 20 minutes or so of the class today just introducing one of the tools which is freely available, and I'll show you some examples of that, and then you can download and on your computer and start designing stuff by yourself. And I'll give you a couple of problems in your next assignment where you get to practice this analytically and also using the full-blown self-consistent solver of Poisson equation and Schrodinger equation. So it solves it self-consistently. Okay? So that becomes very useful. Just to summarize where we were in the last class, we were looking at the specific case of a heterojunction, a compound semiconductor heterojunction energy band diagram, and how do you draw it. And just as a summary of what we did towards the very end of the class on Friday is so we said that we are going to put together two materials, one a wide band gap semiconductor with a doping such that the Fermi level is somewhere there near the conduction band, so that's clearly n-type, and another semiconductor which is a narrower band gap semiconductor and doped p-type such that the Fermi level is near the valence band. And what is the band diagram when you put it together, right? So that's the question we had discussed in the last class. And the procedure to do that was to realize that no matter what are the details of stuff that goes on inside, after you put them together and it forms a real heterojunction, the Fermi level is the same everywhere, right? So that's obviously a nice thing to know right away. And the other thing you realize is because the Fermi level is higher here than in this region, this layer is going to lose electrons, lose electrons, and this layer is going to gain electrons, the same electrons that's lost by that layer. Is that clear? I mean, so wherever is the Fermi level is higher, is going to dump electrons in the other layer. So that's going to happen. And the way the p-type layer ends up gaining electrons, meaning it gets negatively charged, and the n-type layer gets positively charged. But you see that this is really not different from if you had a normal NP diode, right? If you had an N and a P, you remember you got a depletion region on the N side, you lose electrons, and you get positive charge. It's the same thing, except here you can actually see that you can have a situation if this was not the band alignment, but maybe the band alignment was such that the p-type or the Fermi level of this layer was actually higher in the p side than the n side. It's possible, right? You can choose a broken gap heterojunction, right? And you suddenly have the situation that the p-type layer is going to actually just as a side example, that if I choose a situation where I have an n-type layer here and I have a p-type layer which looks like that. This is the valence band of the p-type and Fermi level is there. right? You see, this is N, this is P, but now things have changed completely because now the N layer is supposed to be gaining electrons and get more negatively charged. You see that? I mean, it's very different now, right? Not the same. So that thing happens in a heterojunction. In a homojunction, this can never happen. That, you know, so in a homojunction, if you have N layer and a P layer together, the N-type layer will always lose electrons. The P-type layer will gain electrons. There's not much to do after that. You know, so, but in a heterojunction, by choosing the right band alignments, you can completely change the game here. And here, for example, after all is said and done, you can kind of figure out how the things will look very far away from the junction. The bands will look exactly like what they are here. It's not much change. So this, remember, is clamped because of doping, right? EC minus EF is clamped by doping far away from the junction. Similarly, on the right side, very far away, this is also clamped by doping. You know, it's a narrower gap material, so it's also clamped by doping. And now you can see the way it's going to actually form the heterojunction is somewhat non-trivial and actually kind of quite interesting. So the p-type layer is going to lose electrons, right? But you realize it doesn't have much electrons to start with, right? Right. So how is it going to actually do that? And the n-type layer is going to gain electrons, and it has a lot to start with already, right? So let me just sketch it out how it's going to look in the end. So what you will end up getting here is, in order to lose electrons, whenever you lose electrons, you gain positive charge. And whenever that happens, the band is going to bend up. So whenever there's positive charge, the bands bend up. But I think you also realize that the bands will start bending, but they cannot bend too much. Because once the Fermi level enters the valence band, the DOS is very high. The density of states is very high now, right? So it's going to bend up initially sharply, but then it gets, you know, kind of stuck because very large DOS. And so the band diagram is going to actually look, remember the gap is not changing because of all this stuff. So the band gap is kind of locked to the semiconductor composition, right? So it's going to essentially, so it's going to look, oh, sorry, it just I cannot be somehow, okay, something like that. Okay? It's going to just bend up. And on the left side, it's going to actually bend down. Right? Do you see that? It's going to accumulate electrons that were dumped out of there. So it's going to kind of bend down. So, and you have kind of a broken gap junction here, where these are all valence band states, and then what you will get is, you know, in this little window here, it's a triangular region, and we have quantized states here. So you will get an electron accumulation layer here, and you will get a hole accumulation layer here. So there are, in this little window on the right side, a lot of holes. So what happens here is, this is a very weird p-n junction. Is in a p-n junction, we learned earlier, in a homojunction, you have depletion on both sides, right? Here you have accumulation on both sides. What is accumulation? The n layer has become more n-type. It has accumulated more electrons at the junction. The p layer has become more p-type. Right? So it has accumulated more holes on the p side. Right? This makes sense. So you have a dipole here, but this dipole is a mobile dipole. I mean, basically, the extra electrons and the extra hole gas here are both mobile. Does this make sense? So this is a slightly different sort of heterojunction. And in the next assignment, I'm going to give you a few problems so you can kind of play around with it and see. So you can have situations where there's depletion on both sides, where there's accumulation on both sides, there's depletion on one side, accumulation on the other, and so on. You can design things accordingly, so by choosing the right doping and the band offsets and all that. Okay, and then this sort of design is very, in the last decade or so, it's been, a lot of kind of new device structures have been designed, and they work very well based on this sort of design structure. Okay? So especially related to quantum cascade lasers and such devices where you have interband cascading and things like that. Okay, so again, I mean, this structure, as we had discussed, The one thing that kind of always you can count on, I mean, if you have a standard depletion, then you will have, again, the procedure was, remember, you find the charges, and here we know that there is depletion on the n side, so that's going to give you positive charge, depletion on the p side, so that's negative charge, and they're exactly balanced. And from here you find the field, right? The field was an integral of the depletion region, so something like that. And then your band diagram will be the potential is an integral of the field, and so on. But after doing that, we realized in the last class that it's possible that under certain doping concentrations, so your band diagram might look somewhat non-trivial. And I'm going to, that's the one I'm going to demonstrate a little later today with its full numerical accuracy, and I'll show the tool that we are going to use for that. Okay. So what we had discussed was, again, far from the junction, nothing has changed. Fermi level minus EC is the same. Far from the junction, nothing has changed. EC is the same. But as I come close to the junction, here I see there's a depletion, so the band's going to bend up. Positive charge, the bands are going to bend up. There's depletion, so in a p side, so the depletion region means the bands are going to bend down. So what really we are discussing is you can have various situations depending upon the doping levels and conduction band offsets, right? So for example, I dope, let's say I dope the n side region rather heavily. So I think you realize if I dope it heavily, what it means is I will have a bigger doping density, and therefore the depletion will be smaller, right? And so what happens then is instead of something like that, what you will get is kind of, it'll go up sharply, but it won't kind of drop. So when the band offset doesn't change because of doping, and you might end up with something like this, okay? And then we're going to see that numerically. So I change, and I certainly have a spike in the basically the height of this becomes larger than this height, and things like that. There's a conduction band spike now. It's possible. Yeah? Okay, so was that clear? I mean, just the procedure is, again, first look at the Fermi levels and realize, is it a normal depletion junction? Is it a depletion accumulation junction? Is it accumulation junction? That you should be able to say right from the beginning by looking at the Fermi level location, right? And then from there you can look at the structure, and then the moment you realize that, oh well, I have probably, as long as there's no regions where the Fermi level goes into the bands, the conduction band, or Fermi level goes into the valence band on this side, for example. As long as that doesn't happen, you kind of don't need Schrodinger equation to solve this problem, because it's mostly semi-classical. Poisson equation works well. But the moment this happens, you have this basically a Fermi level, and if you kind of zoom out from here, the way it looks is you have a potential barrier, right? So this is a potential barrier, and here's a triangular sort of potential well, and this is kind of a classic triangular quantum well for an electron, and there may be some bound states inside here, E1, E2. This is a triangular well. We have looked at the square well problem, right? But this is a triangular well. The energies change a little bit. They look like Airy functions and that sort of thing, but we're going to see that now a little bit later today, the numerical solver for that. So that's when you kind of need the Schrodinger equation to make sure that the solution is correct. Yeah. But let me also say that even without Schrodinger, if you kind of don't do a Schrodinger, you do a semi-classical calculation, you still get pretty close to the answer. You get pretty close. Okay. Right, so what I wanted to do was kind of skip over a couple of things here and look at specific cases of these heterojunctions from the point of view of first a little bit on electronic devices, and then we will look at a few things about the optical devices like lasers and such things, and then we'll look at simulations of a few of them in some detail today. Okay. Electronic devices. So the most standard electronic device that or the most widely used is the silicon MOSFET, right? And we know that it's not typically considered as a heterojunction device, but actually it is a heterojunction device because your insulator or SiO2 is a very different band gap than silicon, right? And now it's a high K material and other things like that. So if you look at the energy band diagrams of a silicon MOSFET or a high electron mobility transistor, which is based on compound semiconductors, they look pretty identical, and the physics is very similar. This is really not much different. Okay. So we are going to look at the heterojunction situation because it's very closely tied to what we were doing right now. Just look at the heterojunction. And for the MOSFET, if you have, many of you have had device courses, you have probably seen that. And if you haven't, I mean, the earlier the video lectures that were posted have quite a bit of that discussion on MOSFETs. Okay. So here's an example of a compound semiconductor heterostructure transistor. So they go by many names. So heterostructure field effect transistor, HFET. Or a little more popular in the US, I would say, is HEMTs, the name. HFETs may be a little more in Japan and other places. HEMTs would be high electron mobility transistor, high electron mobility transistor. So the structure is shown here. This is the way it's sketched here is, I mean, like any transistor, you have a source, a drain, and a gate. It's a three-terminal device. And what you have under the gate here, let's look at that part first. Under the gate, what you have is, if you go down, you have N+ aluminum gallium arsenide. Then you have an undoped layer of aluminum gallium arsenide. So let me just sketch the layers out. Okay. So we're looking at a high electron mobility transistor. And the specific case we are looking at is gas, but what I was saying is the physics remains the same, whether you're doing a gallium arsenide HEMT, in-gas HEMT, a gallium nitride HEMT, the physics is pretty much the same. Right? Okay. Here, so the layer structure then is, meaning when you grow it epitaxially, let me kind of go through the process what one would do. So you typically what one would do is first design it, for using your band diagrams and all that, and say, I want this thickness, I want this quantum well there, I want this much electrons in that quantum well, maybe I want just two subbands, two quantized states or something like that. You design it first, and then you grow it. Let's say we have grown it, and here's the structure. We're going to kind of go backwards now. Okay. So we have grown it, and here's the structure. So what you have grown here, after the epitaxy is just looking. Okay, let's start from the bottom. Okay. Semi-insulating gallium arsenide. Okay. So this is something that I will kind of. I'm going to discuss doping even in some more detail when we talk about defects and impurities and other things like that. But semi-insulating gallium arsenide is a very interesting material. Most compound semiconductors that are used for electronics in any way, be it high-speed electronics or high voltage, need a layer which is highly insulating. In fact, if you are doing transistors, of field effect transistors, it is actually not very difficult to make a semiconductor layer conductive. But it is very difficult to make it insulating. This is kind of upside down from what you hear. You always hear, oh, high mobility and high mobility. High mobility is important, but it's not that important, right? Because all like 3,5s, they are, if you look at antimonides, arsenides, you can get 40,000 mobility actually at par with many things that are claimed to be better, or actually even higher than many things that are claimed to be better. But what is extremely difficult to get in materials is controlled insulating layers. So that's the isolation. When you turn off a transistor, this is what's going to kind of make it off, keep it off. And that the usefulness of a transistor is really not its on state. The usefulness is something is on and you can turn it off, right? because a metal will always give you a very high current. There's no problem with the on state at all. Right? The off state is the key, and the semi-insulating gallium arsenide or semi-insulating gallium nitride, indium phosphide, whichever way you look at it, this is a very interesting material. And how do you make something insulating, like a semiconductor? Maybe we can just discuss that very briefly now, because that's a point that's generally not kind of stressed on in many device courses and other things. So how do you make something insulating? How do you make a semiconductor insulating? So, yeah.
Make minority carriers prominent charge carriers.
The prominent charge carrier, yeah. So, right. So you basically have to take away carriers, right? So, and you have majority carriers and you have minority carriers, right? So, so one way to do that is you can kind of deplete away all the majority carriers, right? But I think if you look carefully, there's a very interesting situation here, because whenever you deplete, for example, you deplete it, right? And you're depleting it. And if you are reducing the number of electrons, you are raising the number of holes. That you cannot avoid, right? I mean, because the Fermi level is there or there, right? So what happens then is, just by pure doping, you can do the numbers. You will have a conductivity. This is very hand wavy, but actually it's very reasonable. Q times n times the mobility of electrons plus hole density times the mobility of holes, right? That's the conductivity, roughly. But what I'm trying to say is, now by doping, what you can do is you can make the Fermi level either the moment you start taking the Fermi level away from the conduction band, if it's close to the conduction band, you have a lot of electrons. That's what. So that term is very high, right? N is very high, this is very low. Right? But what I'm trying to say is, as you move the Fermi level, I think you will see that the conductivity as a function of the Fermi level is going to be very high. This is, you can look at it as a log scale, right? So it's going to be very high, and then it's kind of going to drop, but then it's going to come back up again, right? Because you're going to, when this one is high, it looks like that. And or let's say this is EC and this is EV, and when the Fermi level kind of goes close to the conduction band, you have a lot of electrons, right? Fermi level goes close to the valence band, you have a lot of holes, and it kind of looks like that. The minimum level is something you can calculate, and it will be related. I think you can see from here the minimum carrier density you can get in a semiconductor, which is pure and all that sort of thing, or this part here, you'll see that that's actually related to something like that. It's going to be related to something like that, related to the band gap. How far away from the band edges have you gone, right? As a result, the wider the band gap of the semiconductor, the more you can change the conductivity. That is a hard and fast rule. You can't change that, at least as far as we know till today. You can't change that, which means that just by pure doping, if you have a very narrow band gap semiconductor, right, say indium arsenide, you really cannot modulate it much. You really can't, because you can do the numbers, put in the band gap to KT, and for example, if you have 0.3, 0.4 electron volt band gap, your modulation is hardly 3 orders or 4 orders or something like that. You can actually calculate it at room temperature. If you take the temperature lower, no problem, you can modulate it more, but room temperature, the modulation is. So the trade-off is, the same semiconductors which have a very narrow band gap that give you a very high mobility, right? The narrow band gap semiconductors give you very high mobility, right? But then you see the problem, when you're going to turn it off, it's going to have an issue. Right? So if you're using it as a bulk material, right? And if it's doped one type, is N type or P type, whatever, right? But the semi-insulating material changes the game completely. It's a very, very interesting way of making something insulating. Does anybody know what is semi-insulating material? It is, so, yeah, anybody knows? So let's see. So for example, semi-insulating gallium arsenide, what you do is, this is not purely gallium arsenide, and it's doped neither N type nor P type, but it is doped with Typically, for example, one can grow it at a low temperature, sometimes called LT gas, low temperature gallium arsenide, or you dope it with something which introduces states very close to the middle of the gap, middle of the band gap. And the whole job of that state, those states are, and they are mostly what you would call is a, for example, if you look at gallium nitride, the unintentional doping of gallium nitride is the minimum doping you can get in the cleanest MBE or MOCVD systems ranges around maybe 10 to the power 15 per centimeter cube, meaning your doping density is always greater than or equal to this much, 10 to the power 15 per centimeter cube. No matter how hard you try to keep the material pure inside the growth chamber, maybe you can make it better, 10 to the power 14 or something like that. Okay. So what does that mean? Because of unintentional dopants that have gone in, either due to statistical inavailability or during the growth and all that, they've gone into the crystal. So out of 10 to the power 23 per centimeter cube gallium and nitrogen atoms, 1 out of 10 to the power 7 atoms is an oxygen, for example. Cannot avoid that, right? So, and that's a dopant, right? So if you have such dopants and you put in a deep level, say mid-gap states of density, let's say 10 to the power 18 per centimeter cube, let's say, right? 10 to the power 18 per centimeter cube. Then, because of these unintentional dopants, you will have 10 to the power 15 per centimeter cube electrons here, but the job of these defects in the middle of the gap is they're going to basically suck these carriers away completely, just remove it from the band. Okay? And when they are here, they are localized, so the doping density is such that they cannot kind of hop from one layer to another, so they kind of get stuck at the dopant level. The wave function of the electron is very small. These are deep level states, very small and localized. It cannot move, and the temperature is not, because it's so deep, it cannot be kicked out either. Does this make sense? So it cannot be ionized, so it's become immobile. You basically remove the carriers, keep them guys. And you can do the same thing for holes, but it's typically done for electrons, these deep levels. So that is what is called semi-insulating semiconductor, where you've intentionally put in deep levels to remove carriers and make it insulating. Now, the conductivity of, for example, the highest resistivities of, if you look at silicon, the purest silicon possible has, remember, Ni of 10 to the power 10 per centimeter cube, right? This is intrinsic carrier density, thermal generation, purest. Any little deviation, you put in some dopants, your carrier density will always be higher than 10 to the power 10 per centimeter cube at room temperature, right? But if you do something like this, the semi-insulating, you can basically go to 10 to the power minus something per centimeter cube, which means there's nothing left, all the carriers are gone. So you can change, typically, so silicon has really not been used for applications at very high speeds where you need the semi-insulating region, which is why this technology has really not been developed, the semi-insulating technology for silicon yet. And on the other hand, the compound semiconductors started in electronics with applications in RF and high-speed electronics. So there it's extremely important that this layer be very insulating, because if it's not, it's conductive, and you're looking at an RF signal and a wave, it's an RF wave, essentially the electromagnetic wave that goes here is going to kind of couple to this conductive region, and there's a huge amount of loss. So it's extremely important that this region is insulating. And so the insulating nature of how insulating is this region? It's about 10 to the power 8 or more, maybe close to 1 billion times more insulating than silicon, the best insulating silicon today. So that's how much we're talking about. Very, very different in that sense. So that's semi-insulating, and that's how you do it. And I think you can kind of see that the way you're doing it is a very interesting way, that you essentially put in deep levels and you kind of localize the carriers. You cannot move anymore, basically. Okay, so that's your semi-insulating gallium arsenide. And this is a very important thing about used in RF electronics and all that. Okay, so after the semi-insulating gas, what you have now is the undoped gallium arsenide region. Okay? So let's say an undoped gallium arsenide region, and then you have a very thin layer, which would be called a spacer layer, for example, of undoped aluminum gallium arsenide, maybe 30%, let's say, for argument's sake. Right. Remember, there won't be much strain here because gas is kind of almost lattice matched to gas, right? So we looked at that. And then you have a layer of doped, okay, so what you have is a layer of N plus aluminum gallium arsenide. So let's say the doping density 10 to the power 18 maybe, and we will look at some of the simulations today. Okay, so it's about 10 to the power 18 per centimeter cube, and you cap it off with an N plus gallium arsenide. So the layer structure looks like something like that. N plus gallium arsenide. And there's a purpose for each of these layers. There's a reason why each of these layers has been grown that way. Okay, yeah. And we're going to kind of dissect that right now. What's the reason? I already told you the reason for insulating layer. Okay? So this layer you can buy in the market today. Maybe a 4-inch wafer of semi-insulating gallium. So you buy that, and you kind of put it into the MBE system in Phillips or Duffield, and you kind of do the growth. Yeah. Right, so just as an example, many of these initial structures were, a lot of the initial HEMTs in arsenides as well as gallium nitride were done in Phillips Hall here. So a lot of the early papers, if you read, were done, work was done here at Cornell. Okay, so there was work at Illinois and Bell Labs and other places as well. But yeah. So okay, so this is what you have grown. But you look at the structure of the device, it looks slightly different. What it is, so after the growth, you kind of take it to the clean room and you do some lithography on it. And the way that you're going to make the device is you're going to etch it down to, let's actually erase that a little bit. You're going to kind of remove this part of the region, okay, and then go there. It's going to remove those regions. Okay. After the growth, you go, put a mask and do a optical illumination, remove the mask, then etch it. But etch and then stop here. Don't go all the way. You stop. It's very important where you stop. Very important where you stop. Because that's going to control the threshold voltage of the transistor and all that stuff. Okay. And then what you do is you put down again by e-beam evaporation or some sort of method. You put down metal contacts, and this will be your source contact. This will be your drain contact, and you will have another deposition step, which will give you your gate contact. This is the gate. So then this is your HEMT, for example. So, HEMT or high electron modulated transistor. Okay. So that's the process. Now let's kind of dissect what's going on inside here, the way it was done, and the reason all that stuff comes from. Now you got to look at the band diagram and what's going on in the band diagram. Okay. Yeah. Before we do the band diagram, let me just kind of summarize the idea of the transistor. This is not really a device physics course as much of a materials course, so we're looking more at the fundamentals of the materials, but what we are going to see now is the reason it was grown in this structure was grown is because the whole structure is going to give you a very high mobility, two-dimensional electron gas in a quantum well at that interface. That's the reason it was grown that way, and that it was designed actually in the beginning in that fashion. So this 2D electron gas is kind of all over around, and we're going to actually look at an energy band diagram kind of going in this direction now. So we're going to look at that. These electrons we'll see are because of charge transfer. Basically it's kind of like this, kind of. This is a 2D electron gas. It's kind of like that. Okay? And these electrons are sitting above the Fermi level. The electrons are sitting above the conduction band edge here. And you can, if you take N-type doped semiconductor, if you take an N-type doped gallium arsenide, right? So, so you have electrons in the conduction band because of thermal activation, right? Heat kicks it out. But if you take it down to very low temperature, you lose all those carriers. They'll exponentially decay. They'll fall back. Here, you can take it to any low temperature. The electrons will never go away because they're not because of thermal activation. They are because of electrostatics. Basically, electric fields have kind of created it, and electric fields don't depend on temperature. So it's not because of electrostatics. So you can take it to, 20 milli or microkelvin. The 2D electron gas is still there, and that's where all these big discoveries in quantum Hall effect and in condensed matter physics came from, because the electron gas stays at the lowest temperatures and all that. It doesn't go away. So this is the 2D electron system. It's called so there's no freeze out. And now you can see that you can actually choose your kind of the barrier material and the electron gas, where the electron gas sits. You can choose it. You can choose a very low band gap semiconductor, indium arsenide, a large band gap semiconductor like gallium nitride or whatever, and you can choose the mobility, material based on the mobility. So you can choose a superior channel material, and you can design it for high densities and all that sort of thing. Okay? But the key requirements, the most important requirement for a HEMT is not a high mobility actually. It is the fact that you must have a semi-insulating substrate. Without that, you don't get off the first base. I mean, it's basically, there's nothing to do if you don't have a semi-insulating substrate. And that's where this is something that a large fraction of the community doesn't quite realize, that this is the key. Semi-insulating substrate, and then more important to make it insulating than conducting. Very important. A large band offsets, the larger is the band offset here, the more electrons you'll be able to fit into that quantum well. Just purely, if you remember, the number of quantized states and all that stuff depends on the barrier height, right, in a quantum well. So just based on that, larger is the band offset, the better is the carrier confinement. And high mobility, once you have a semi-insulating substrate and you have a decent mobility, the second most important thing is a low resistance contact, an ohmic contact to this. So we are going to make source and drain contacts, and the reason we have grown this in that structure, there's N plus gas and all that on the cap layer on the top, is because you want to get a low resistance ohmic contact. That's the reason why it has been done that way. And this is, though it's listed last, but actually it's equally important, that your gate should be completely not in electrical connection, meaning the conductivity between the gate and this 2D electron gas should be as close to 0 as possible, meaning the electrons cannot flow from this to this. It can only capacitively couple to that. It's a capacitor. But there should be no conductance between the two. That's, if you have a conductance between the two here, then you have basically a 3-terminal resistor. There's no gain in that. It's not a transistor. And you kind of, still today, you will read papers where it's clear that it's a 3-terminal resistor, but people claiming it to be a transistor. But you guys know you should never say that, because the moment you have gate leaking as well as the source and drain, there is no gain in that system. It's 3 resistors. There's no gain in 3 resistors. They're all passive elements, right? The gain comes if the gate is coupled capacitively to the electron gas, but there is no electron flow here, because the gate can now control the resistivity of that region without flowing electrons into that region. So it's remotely control the resistance of this channel, right? It can remove or accumulate more electrons in that region. So it remotely controls the resistance of this, and that's, again, the origin of the name transistor. It's a transferred resistor. So this is a resistor between source and drain, but the value of its resistance is not controlled by the voltage you apply on the source or drain. It's controlled by the voltage you apply on the gate, right? And there's no current flowing into the gate. So it's a remote kind of, so the resistance of this channel has been transferred to the gate. The gate controls it. And how much does it control it? It controls it by 8, 9 orders or 7 orders of magnitude. So that's the origin of gain of a transistor. Okay, so all these things are extremely important, but I think I kind of said that in a realistic technology, if you go to a venture capitalist, I have a great idea for a new HEMT, they're like, well, do you have the semi-insulating substrate? That's the first question. If they're a good venture capital, they'll ask you. And then others come later. Others, okay, yeah. So let's look at the choice of materials. We are looking at gallium arsenide, and say 30% aluminum gallium arsenide, right? So we look at the band gap, gallium arsenide, 1.4 electron volts. 30% Al gas would be kind of somewhere there, right? That's the band gap, almost lattice matched. You know? Based on this idea that I think we kind of pointed out, because of these requirements, there are the HEMT technologies have been developed for gallium arsenide, for indium phosphide, for gallium antimonide, and indium arsenide. These are the material families for which HEMT technologies have been developed today, and then obviously a big new one, which is gallium nitride. So these HEMT technologies have been developed for all. The first thing that was done is you make this a substrate semi-insulating first, and then grow large area substrates. That has already been done for gallium arsenide and indium phosphide. Gallium antimonide kind of being done. Gallium nitride, large area substrates have been hard, but luckily people have been able to put it down on all kinds of other substrates like silicon carbide, but it's coming along as well. You know, it's a little harder to grow. And the second half of the course, we are going to discuss a lot about the growth. You know, what are the challenges in growing gallium nitride versus gallium arsenide and all these things. We're going to discuss quite a bit of those materials challenges. But given that you can create it, so I think you can kind of see gallium arsenide based structures. So the way you will use it is the quantum well will be gallium arsenide typically, and then the barrier would be something with a wider band gap, aluminum gallium arsenide or something like that. Something like that, right? You go up. Indium phosphide base. So indium phosphide, very interesting material actually. So with indium phosphide, what you do is your substrate is semi-insulating indium phosphide. Indium phosphide band gap is kind of around gallium arsenide, about 1.3 electron volts, something like that. Yeah. But that's just the substrate. With indium phosphide, the way you make a HEMT is you choose a lattice matched substrate, which is indium, along this line, indium gallium arsenide, which is around here. So your band gap would be about 0.7 eV or so. We'll put and what you do is you put a quantum well. You can grow thick because it's lattice matched, but put a quantum well typically. And then your barriers are, you can use indium phosphide, but that's rarely used. What is actually used is you want a larger conduction band offset, which means you want a larger band offset, a band gap difference between the two. Right? Indium phosphide gives you kind of a nice band gap difference, 1.4 minus 0.7, so about 0.7 electron volt, out of which about 70% goes to the conduction band. Right? When we had seen that. So that's the band gap difference, 70%. So that would be about 0.4 eV or 0.5 eV, right? Band offset. But you can get even more by going to even slightly more by going to, instead of indium phosphide, you go here, and that would be an alloy of indium arsenide and aluminum arsenide. So that's indium aluminum arsenide, slightly more. Right? But what happens is typically today in many of the HEMTs made by many companies, Analytics, RF Micro Devices, they use indium aluminum arsenide as the barrier layer because the band offsets are actually it breaks the rule of 70-80, so it goes a little more in the conduction band. So you get even larger, deeper well, which is why one of the most popular technologies today is in-gas channels with indium aluminum arsenide barriers. So the channel has this gap, the barrier has that gap, and you have a very large difference in the. So that's used heavily these days. And the kind of even faster devices with higher mobilities are based on 6.1 angstrom materials. This is gallium antimonide based. But people have had a hard time growing bulk single crystals of semi-insulating gallium antimonide till now. But there's a need for it because you want to, the highest speeds are actually available in this particular material combination because the gaps are low and all that. Right? So here, because you have heterojunctions, you can play a very nice game. You can change the bulk band gap of, say, indium arsenide is 0.3 something electron volts, right? But in a heterostructure design, you are not limited to the bulk gap, right? You can quantize it. You can increase its band gap by shrinking the quantum well width and pushing that energy level up, right, in the conduction band, pushing it down. So you can design the band gap according to what you need. So as a result, this combination of 6.1 angstrom large lattice constant semiconductors, compound semiconductors based on antimonides, gives you actually the fastest HEMTs today, some of the fastest actually. But the problem is because the gaps are so small, the modulation is weak, and that's so there are some problems, and the breakdown is also very weak. Remember, we discussed that if you look at even a PN diode, the breakdown is related to the gap very sensitively, right? The breakdown of the device. So it's smaller the band gap, the smaller the breakdown. And in RF application, that becomes a problem because the more voltage you can apply, the more gain, more RF power you can generate, and that sort of thing. Okay, so this is used, and then gallium nitride is used, and we'll discuss that as well. Okay, so let's look at this specific band. So I think I had one slide showing a realistic industrial design today. So here's what I was mentioning. Yeah, that's right. So this is a kind of a zoom out of a RF 80 gigabit per second multiplexing IC. So it's basically for high speed 80 gigabit per second. Typically, one would be looking at I think your cell phones don't use this right now because cell phones are like 4 gigahertz max. But an optical link where you have optical fiber and all your data coming in as optical pulses, right? And then you need a modulator, demodulator. Essentially, the photons come in with all the data in an optical fiber, right? Ones and zeros. But then you need to kind of detect them, and so this is typically used in such an optoelectronic converter. And this is a HEMT with the indium phosphide substrate, semi-insulating. Then you look at the layer structure. Look at the let's see, where is the quantum well here? So by the way, this is the device design. Here's the gate metal. I've drawn it like a rectangle, but actually it looks more like a mushroom or a T-shape. And there's a reason for that. Is reduction of parasitics and improvement of speed and all that. It looks like a end of a T here, right? And then the gate length here at the bottom of the footprint is about 100 nanometer, 0.1 micron from source to drain. And the design here, if you kind of zoom in here, you look at, you see there's indium aluminum arsenide, as I was mentioning. Indium aluminum arsenide is the barrier layer. And indium aluminum arsenide. So indium gallium arsenide is the quantum well region. So this is indium gallium arsenide, and that's where your electron channel is actually sitting for the conduction. And there's all these details. Here's how the transistor looks, and this is actually used often now. Okay, so looking into the structure in a little more detail now, what's going on already? I think we're running. I wanted to run the simulations, and I will do that now. Okay, so if I kind of go into the structure now along this region, so I have n plus. So I'm going to draw the energy band diagram along two directions. One is here, and the other is here. And we'll see why we have this region, because it will help us in the ohmic contact, and why we have this region, because it helps in the modulation of the transistor. So again, our Fermi level, I'm going to just draw the band diagram underneath here first. And then very far from the, deep down inside here, the gallium arsenide is undoped, and the Fermi level is kind of getting close to the middle of the gap. But by the time you reach here, it is in the middle of the gap, because these are mid-gap states. The Fermi level is pinned in the middle of the gap in the semi-insulating gallium arsenide. Okay? So I'm going to just look at that situation, and then as you come close to the surface, to the heterojunction, so you have gallium arsenide here and Al gas here. So if you look at the structure, there's an undoped layer, typically about 5 nanometer or something like that, and then there's a dope layer of Al gas. Okay. So the undoped layer, and let me kind of sketch the band diagram first, and then we look at all the details of how and why that happened, because it's an iterative process, as you realize. So you have band offsets of delta EC and delta EV. And then there's an undoped layer of about 5 nanometer. And the thing about Al gas is across the junction, the slopes of the conduction bands would be the same, because the dielectric constant is about the same, and there's no interface charge in between them. So for about 5 nanometers, the Al gas is undoped, this region. And so if it's undoped, there is no fixed charge there. There's no net charge there, so the field cannot change. The field will remain constant. Right? Okay, and as a result, the band will bend linearly like that. It's going to look something like that. And then you have doped region here, 10 to the power 18, and this region will be depleted. The region, the whole, why is it depleted? Because these dopants had electrons in them, but before you put this two in a heterojunction together, if you look at it, so you have Al gas, you have gas, valence band, conduction, valence band, and the dopant levels are very shallow. They are close to the conduction band of Al gas. Okay? And here's the conduction band of gas of the narrow gap region. No dopants here, but the dopants are sitting here, and there's about a 5 nanometer spacer region in between. Right? That's what we have done before. And you see the Fermi level of this was kind of here. Fermi level of this is maybe kind of here, and you can right away see this is going to lose electrons to that. Where did those electrons come from? They came from these dopants, right? So this region, which was doped, is going to be depleted, and is going to dump all the electrons there, right, into the narrow gap region. And this idea is called modulation doping, right? And very, very important development in compound semiconductors, modulation doping. All that it means is the place where the electrons are actually moving, the dopants are not there, they're somewhere else. As a result, the scattering, because of them, the mobility reduction you get because of scattering, because of dopants, is very low. You don't have much scattering. As a result, the mobility is very high, because of this region. That you have removed the source of the electrons from the path of the electrons. So they're not, because the electrons are going to move this way, they're not going to go towards the dopants anymore, and the dopants are sitting far, and their Coulomb potentials that scatter the electrons is very low now. So it's modulation doping. So, okay, with that, what you end up getting is you get an electron gas here, but then because this is depleted, and it behaves just like any other depletion region, the band starts bending, and it will actually kind of bend like that. It curves that way. Whenever you have positive charge, it curves always that way. And then if I look at the gate, I've actually given it a very thin region, and I put a metal here, a metal directly on the on that N plus region. So that's my gate metal now. So that's the whole band diagram under the gate. What do you have? You have a depleted insulating Al gas region, and you have an electron gas sitting here. It's a two-dimensional electron gas now. It's sitting very close to the gate metal, and this, sea of electrons in the metal and the electron gas here are coupled capacitively. It's a parallel plate capacitor. That's all there is to it. I mean, it's a parallel plate capacitor between the 2D electron gas and the metal plate. So as I change the gate voltage, I think you know that the amount of charge in the, let's say the sheet charge is Q times Ns. The charge in any capacitor is the gate capacitor times the gate voltage, right? I mean, that much you know. Charge in a capacitor is capacitance times voltage. Okay? So that's very. But here we will see that there will be a threshold voltage here. This is rough order. So as I increase, for example, the gate voltage, I can increase the carrier density. If I increase, meaning if I make it more positive, if the gate voltage is more positive, I pull it down. I pull this down. It gets deeper. You get more electrons here. What's going on is actually you're moving electrons out from the metal, putting it into the 2D electron gas. So that's okay. So all right. Just to look at the situation here, you can see if I were to. So I'm not going to kind of get into the details here. You can look over the slides. I'm kind of putting that up now, and you can look at how the electron gas is controlled by the gate voltage. You can completely calculate based on the band offsets and all that. What is your threshold voltage? It's, and the doping and all that. You can kind of completely calculate that. Another trick that is many times used is instead of doping this entire layer N-type, you can dope it only in a very thin region very heavily, and that's called a delta doping. So in that case, your band diagram will look something like that. It will look very with a triangular shape. You have doped only in this window, not everywhere. So you get a curvature like that, and that's what's shown here in this particular junction. And once you know your charges, you can integrate it, find the field, then find the band diagram. I mean, that's the same game, right, as in a PN diode. And I'm going to skip over a couple of these things here. So, for example, there's a triangular well, and you can kind of, what you can do is kind of write down the energy conservation starting from here. You climb up a certain Schottky barrier height, then you drop a certain voltage because the field times thickness is the voltage. You rise again, drop conduction band offset, go up, and you kind of know that you are back at EC minus EF or something like that here. So from that relationship, you can find out at what is the carrier density dependence on the gate voltage. You can kind of relate it directly. And it's going to be a effective capacitance times the gate voltage. And then from there you can find out at what gate voltage does this effectively go to 0, and that is your threshold voltage, which is standard stuff. Nothing very fancy in that. So what we want to do now is, that's the band diagram under the gate. And just, again, whatever I'm saying now, you can do it in great detail, calculate it accurately, but just from a pictorial perspective, when you apply, if you have electrons in the 2D channel here, two-dimensional channel, what sort of a gate voltage should I apply to turn the transistor off? Positive or negative gate voltage here. So I have electrons here which are going to conduct because they are in ohmic contact, meaning very low resistance between these two. So this source is connected with a very low resistance to this entire 2D electron gas. So the moment I apply a drain voltage here, say about 0.5 volts, let's say, and this is typically grounded in most applications. Okay? So there'll be a current that will flow here. Right? Now I want to turn the thing off. Right? What voltage should I apply on the gate? Positive or negative? Negative. That's very clear. I mean, that's your intuition says that, yeah, I have negative charge, I want to get rid of it. You apply negative voltage. It's very clear. And what happens when you apply negative voltage is you have a metal plate, which is the gate metal. You want to charge it negative, so you have to put more electrons on it, right? Where the electrons going to come from? They want to come from here. I mean, the battery is not providing you charge, right? So what the battery is really doing is you have a gate. So what we're doing now is we are kind of tied. Everything is grounded in the end, right? So what this battery is doing is essentially pulling electrons out from the 2DEG and putting it into the gate metal, right? So that's really what's going on. In the band diagram, what's going on is when you apply negative voltage, this band starts, you kind of pull the metal Fermi level up. Negative is always up, positive is always down. Right? And you can think of it as the density of states. Your negative voltage means you're putting more electrons, so the Fermi level is going up. That's the way to look at it. So when you pull it up, it basically, all this stuff is locked. I mean, the band offset doesn't change with gate voltage. No, so essentially what it does is it starts, the Schottky barrier height doesn't change with gate voltage. It starts pulling the whole thing up now. Okay? Does that make sense? Okay? So you can see you're pulling the conduction band minima here above the Fermi level now. Right? And then you're emptying out the electron gas. That's the switching off of the device. And on, or you want to, if you apply positive voltage, you make it, as you can see, you pull the whole thing down, because band offsets and Schottky barrier heights do not change with voltage. So when you pull it down, this kind of will go like that, and the quantum well will get deeper, you get more electrons here. Does it make sense? So, and that you can completely calculate self-consistently solving Poisson and Schrodinger, but you can do a lot just by writing analytical equations, and they take you pretty close to the correct answer without going through all the details of the problem here. Okay, so there's I was planning to finish one more thing here. I forgot to say, what happens under the gate, right? That's very important as well. I didn't sketch that. So let's just look at what happens under the under the source and drain. So under the source and drain, what you have done is you have actually a reasonably thick N plus Al gas and then a N plus gallium arsenide. So there, what you have is because there's kind of a little more electron gas here, so you have even more electron gas density. And all right, let me just erase that. So the surface is N plus gallium arsenide, and the reason for that is you have a very narrow Schottky barrier height, and you have a good ohmic contact. So I'm kind of sketching the band diagram along this direction now. So here's the metal of the drain, let's say, and then you go to gas, and there's typically a slight depletion. So it looks a little more complicated, but the whole game for having a very high doping and a thick layer is what you end up doing is in this region, you end up putting even more electrons. I mean, there are electrons here now in the conduction band. The conduction band edge of the Al gas region here goes below the Fermi level. So you have a pool of electrons here, a pool of electrons here, the thin barrier for tunneling, so electrons can tunnel through. And actually, if you look at this barrier, this is also becomes very thin, by the time you reach here. So that's how you can see it's a rather difficult process to kind of connect to the electron gas with a low resistance, but this gives you much lower resistance than otherwise. I mean, if they did it by other techniques. For even higher performance, people don't use this structure. What you do is you kind of grow this structure. So you see, I mean, this is the ohmic contact. Here, you don't want to modulate this electron gas. You don't want to capacitively couple to it. You want to couple to it conductively, direct conduction. So it's kind of designed for that purpose. Recently, a lot of high-end devices, what they're doing is instead of doing sort of multiple tunnel processes like that, you kind of etch it down after you have grown the structure on both sides, source and drain, and you kind of regrow here a heavily doped N+ region, regrow. Put it back in the MB, mask it, and grow a kind of a lot of electrons, and they connect directly to the sides, and this gives you much lower resistance than the other. So this regrown contact, it's more expensive because it needs extra epitaxial steps, but it's performance. So performance, it gives you a boost in the performance. And this technique is actually used in silicon too. They grow the MOSFET, they create the MOSFET and then etch down, put it in a UHV CVD system, and regrow silicon germanium region for the contacts in a silicon transistor process today. So the contacts are all regrown. And one of the reasons why the contacts have become so important, and it's important to lower the resistance, is because the devices have gotten so small. The resistance is now completely determined by outside. I mean, the channel is very small now, at 100 nanometer, 50, 12 nanometer, 15 in silicon MOSFET. So all the losses and resistances are kind of there. So you need to do something to prevent that. Yeah. Okay, so one of the things I wanted to talk about also today, but I think I'll skip that, and is the aspect of gallium nitride, which is polarization and the effect it has on all these heterojunctions. Okay. I'll skip that for the next class because the last 15 minutes what I want to do is look at this band diagram solver, okay, and look at a few examples with you. And what I would suggest is if some of you have used it earlier, that's great. But if you haven't, for this course, I'm going to require you to pretty much go here to one of my colleagues back at Notre Dame. He has a software here. You can just download it. Be it, he has for Mac, for PC. It's free. And what it does is basically it takes any structure you give it, like this, like that, whatever, and it will solve the band diagram for you, the whole band diagram, numerically. And the nice thing is what it'll do is it will solve Poisson equation, and if you ask it, it will also solve self-consistently the Schrodinger equation. It'll solve the whole thing for you, and then you can generate your band diagrams that way. There are many other tools, but this is kind of 1D. So the reason it's called a 1D Poisson tool is because it solves it in only one direction, right? So one-dimensional Poisson equation. And there are more fancier ones available. So it does. So let's see. I was going to demonstrate. Yeah.
Is in your website?
I will send out and I'll put it on the class website too. Okay. So you can download it. Okay. So when you download it, it will basically show up as it's very minimal. It shows up as a little app, yeah. So and then let me just. Okay, that's not what I want to. 1D Poisson. So for example, on the Mac, it just shows up like that. You just click and it's an executable. So it'll just start like that. So you can see it has a few things here. But what I want to do is show you that obviously the program needs a materials file, and that is it downloads it into the directory. So let's look at a materials file, and then it will give you some README and some materials file information here. So just please read that up, and let me look at the materials file. Oh, where is them? So let's look at materials file. So here's the materials file, for example. So everything we have done about the band structure, about doping, about band gaps, all that stuff is here. Effective masses, everything is inside here. So for example, gallium arsenide, so it's a binary semiconductor, and so there's a formula for it. So this is kind of the zero temperature band gap, and then as you change the temperature, the band gap kind of shrinks a little bit and all that. So at room temperature, about 1.4 eV. And it has all these properties. The effective mass of electrons in the conduction band is 0.067. So that's the conduction band effective mass for gallium arsenide, and so on. Heavy hole, light hole, all that stuff. Now ternaries, a compound semiconductor alloy, AlGas on top of gallium arsenide. Here are some of the properties of it. The band gap, e.g., changes with the composition X, right? It goes from gallium arsenide to aluminum arsenide in certain ways. So it has all this information. It has, very important, new materials, semi-insulating gallium arsenide. This is important because, as I mentioned, it enables HEMTs. So semi-insulating gallium arsenide, indium gallium phosphide, used a lot for solar cells, right? Indium arsenide. And this is completely editable. You discover a new compound semiconductor today, you add it here. So just add it and run your program. So indium phosphide, gallium nitride. So I think it has evolved. The stuff at the bottom is kind of the newest materials. So of course, you can put it on the top. But okay, so that's the materials file. Now let's do a couple of demos. So I actually had planned to show you very simple, say a homojunction diode first. So what is the input file? Very, very simple. It's just, these lines. This is how you're defining your layer structure now. Right? So here's a gallium arsenide diode. The substrate is, we're saying it's ohmic contact. I have an ohmic contact on the bottom, cannot be semi-insulating then. And then I have 1E16 doping, 5,000 angstroms. It takes units in angstroms. It's an order of magnitude more advanced than a nano. So, okay, 1E16 doping, and then 500 nanometers or 5,000 angstroms of p-type doping, Na, 1E16. And then you have a surface. Very simple PN diode, right? Donors at the bottom, acceptors on the top, so p-type on top and n-type on the bottom. And it has various options, but if you put a star in it, it means you turn it off. In a normal PN diode, you don't need to turn Schrodinger. So you don't solve Schrodinger. Define the temperature at which you are simulating at 300 Kelvin. dy is the mesh size, of your length. If you are 5,000 angstroms, then your spacing is 5 angstroms here. If it's solving for every 5 angstrom. And what you'll do is go in at every point, say here's the band gap, and then 5 nanometers, 5 angstrom later, here's the band gap, here's the doping, here's the band gap, here's the doping, and it will electrostatically solve the electrostatic problem first, the Poisson equation. And if you had asked it to solve Schrodinger, it will solve it too. And the boundary conditions are kind of described by voltages at the two ends, V1 and V2. It's 0 here, no bias, 0 bias condition for a PN diode. So, so what you do is, the way you do is basically you just say, to run it, here's the name of the demo, homojunction diode, right? And so you go here and just say select and run input. So, and just say demo, homojunction diode. Hopefully it'll run. Okay, so it's pretty fast. This is no Schrodinger, so it calculates it very fast. And it gives you a little convergence error. Please read the manual. It tells you what it is. If it's below, it's -6, it's very good. Basically, the resolution here you can trust is 2.3 micro EV, 10 to the -6 EV. So you can trust. And if you are looking for features below 2.3 micro EV, this is not a good simulator. That's what it's saying. Okay, so now it has generated, what it did was it actually generated files here. There's output file, and there's a status file. the output file gives you kind of a list here, which gives you, the band diagram, the electric field, the doping, everything there. Right? And you have to use some sort of a software to plot it now. It gives you, as a function of y or the distance, all these things. And here's a plot. So I have used origin here. So homojunction, where is that? Homojunction diodes. All right. So here's how it looks. Here's the band diagram. So let me just first say, so for example, we looked at I think the screen is rather small. Okay, so here's where I've imported all the data, right, that was output by that file. And let me just do it all over again. So demo homojunction diode output, so that's what it is. It just imported all the data here. And then here's the band diagram plotted for Y, EC, and then here's the band diagram, P on top, N on bottom, energy band diagram, band bending, built-in voltage, everything is there right now. Look at the carrier densities. Well, carrier densities, holes on the top, P side, depletion region, and no holes in the bottom, minority carrier. If you plot in the log scale, you will see the minority carrier density has done it correctly. Electrons at the bottom, N-type, and then depletion, and then nothing on the top, minority carriers here. Right. Electric field, I think we have done that many times. You see, it looks triangular like we have done before, but there's a little bit of broadening at the edges. This is because of this Debye length. There's a finite. The depletion edge is not very abrupt. There's a kind of, and we neglect that in a normal analysis, but it shows you here. Okay. So what you can do obviously is you can go in and say, well, I want a much heavier doping. Let's say I change it to 1E18 from 1E16. What do we expect to happen? The depletion region is going to shrink, right? The field at the junction will go up. The band will be much sharper, right, and all that. So, so you kind of do that, and so let's look at that. This is a homojunction diode. All right. So let's run. Oh, this is even better for whatever reason, I don't know, but yeah. And then we input it or import it. Homojunction out. All right, it did. And see, stuff has happened here, right? The band has gone sharper. I mean, yeah, this is what you expect, and it does what you expect. The carrier densities have gone up. I had only plotted till 16, but now you have 10 to the power 18 carrier densities on both sides. So it doesn't, you can rescale it and see that. But what I'm interested in more is in the field. And look at the field. It has increased by a huge amount at the junction. Right? The electric field has gone up from a few, 20 kilovolt or so to, if we rescale it, let's go, 200 kilovolts. Okay, so it's even more than 200 kilovolts. You see, I mean, the max field has gone up a lot. Okay, so that's fine. That's homojunction. For homojunction, you really don't need 1D Poisson-Schrodinger. I mean, that you can do analytically. Right? Where it gets interesting is in the heterojunction now. Right? So let's look at a heterojunction. So the heterojunction diode, let's start with a heterojunction diode. All right, here you go. So what we have done here is just a plain heterojunction diode, pretty much exactly like what we did here. So we have a gallium arsenide N-type, but we have indium gallium arsenide P-type with 20% indium. So it's a narrower band gap material, and that's P-type on the top. So I have still turned off Schrodinger, but I'll now turn it on and see what happens. Okay, so we run that. So demo junction diode. All right. So that's fast, and heterojunction diodes. So I had plotted this before coming to class, but let's re-import it. I think it's the same thing, obviously, but I'll change it now. Okay, so heterojunction diode out. All right. So yeah, you can see now there's a the top layer has a slightly smaller band gap, right? You can see the band offset here, delta EC, delta EV. And if you look carefully, there will be a little change in the electric field because the dielectric constants are not exactly the same. It kind of takes care of that. Okay? So that doesn't look too different from a standard homojunction diode, right? But when it starts looking really different is when you increase the band offset or you change the doping. That's when things start looking very different. Let's make it much larger band offset, maybe 0.4, and let's say we dope one of the layers 18. Let's say we just. I mean, you can do it whatever you want. I'm just picking this as an example. So demo. So ran over, and then let's look at what happens to the band diagram now. All right, see now what has happened. It looks a little bit like that, right? You see the band has gone down here into the Fermi level. So there's a quantum well formation on the left side. You see that? But you know now that from here, and then you can look at the fields and the charges and all that. But you remember, because you have formed a quantum well, I better turn the Schrodinger around now, right? Because otherwise it's not accurate, because it's solving it classically, but actually it is a quantum mechanical, problem within that little window here, right? So I can decide that I want to turn on Schrodinger only between, say, this point and that point, or something like that. Yeah? And so that would be maybe 40, I don't know, let's say 4,500 to about 5,100 or something like that, let's say, right? Let's go back and turn it on. So, okay, so 40, we don't need 4,000, so let's say 4,400 or something like that. Okay? And now it's going to run the Schrodinger, and all right, so sometimes if it doesn't see enough KT confinement, it complains, and it has what Greg Snyder calls old man's danger signal, because there used to be some TV show in which this was the stuff that a robot said when things went wrong. but that's fine. I mean, that's you can change it if you want, but there's no need to. It's fine. It has calculated things fine, and you can kind of import it now, and it will look very similar in the band diagram, but if you look carefully at the charge, it's going to be different, because the okay, so the charge profile, I think it's hard to kind of see it now, but anyway, if I rescale it, just in interest time, just it will kind of smooth out everything. It won't be a classical particle where the moment you have a barrier, there's no charge anymore. So it's going to actually have decay, because remember, there's a penetration of the wave function into the barriers, right? We had talked about that in detail, and it calculates that. Yeah. Okay, so there are a few more things. Obviously, if you look at, for example, you can put a quantum well, okay, and I'll just show you the figures now. You can run that, and I'll make these programs or some of these available. So, quantum well, for example, it's a very simple quantum well, okay, very simple quantum well with delta EC and delta EV, right? But what it does for you is numerically calculates how many bound states there are. It will calculate all that stuff that you are doing in your current assignment. Don't use this for the current assignment. But it will calculate all that stuff for you, both conduction band, valence band, whole states. And where are those information sitting? You go to status, let's say. So here are all the electron eigenvalues and hole eigenvalues in that quantum well. Four bound states, okay, starting at 0.38 eV to 0.6 eV. So 0.38 eV is the lowest state. Then you have 2, 3, and 4. 0.6 eV is just very shallow, and then it goes out. It's not bound anymore. Okay. Similarly, a few finite hole states. Sure. And then you can obviously, the more interesting structures you can design, you can put this in, calculate your band diagram and all that. Let me show you a couple. For example, if you're designing some sort of a optical waveguide or something like that, here's a design. It's an interesting design which has many regions, some for light confinement, some for electron confinement. Okay. So for example, you want light to be confined here, but the electrons to be kind of confined there. That's a design that's heavily used. And so this is a classical electron distribution in that region. Wherever there's a barrier and the Fermi level, all right, so you see the conduction band here, and the Fermi level is hitting the conduction band. In a classical physics, the carrier density goes to 0 immediately, right? But if I turn the quantum on, it will kind of smooth out very nicely. And that, sorry, what was that again? Demo of optical, right? Oh no. Did I just close that? I think we are running out of time, but we're almost done. Demo quantum well. Okay, here it is. The way it's created is you can create, if you have a 100-period superlattice, you can put in all these kind of repeat codes and all that. And so you have 2 times of 3 times of this thing. So for example here, 2 periods of this 3-period thing. Right? As you saw, there are 2 there's kind of a 3-period 1, 2, 3, and they're repeated twice here, for example. Okay, so, oops. What I was going to show is because the Schrodinger has been turned off, you see this carrier sharp profiles, but those are not real because as you turn the Schrodinger back on, you will see that they actually smooth out very nicely. All right. Oops. No, now it's crashed. All right. Anyway, I'm going to not do that anymore. I think we're out of time. So the last thing I would show is in a real design, for example, in our group's research, we're trying to make these deep ultraviolet structures for light emission, lasers and all that. The band diagram starts looking very interesting. So you get, here's a band diagram calculated with 1D Poisson. You have all these kind of superlattices, quantum wells, active regions, PN diode, but with a very large band gap. And if you zoom in, for example, into a very small window here, this is actually a superlattice that is meant to inject electrons into this region. And if you zoom in into that region, here's how the bands look. So there's a lot of detail that goes in, and these structures are grown in this way. We kind of control it at every nanometer, a couple of nanometers, design it that way. But this tool, I'm going to, again, as I said, I'll ask you to use it and get comfortable with it. It's actually pretty powerful for 1D design. And it tells you a lot of answers that we have been discussing. Okay, good. And I do have the office hour 3 to 5 p.m. today, upstairs in 326 in Boston.